let's simplify things a little bit, okay? Here's our situation. We've got, and I'm just looking at it side on, I'm just interested in the forces, so I don't need the whole 3D picture, okay? As we already know, so you got gravity, that's fine. Okay, and you got the normal force. And in our ideal world situation, we imagined what would happen if those all exactly cancelled out. Okay, if you were traveling at the perfect speed and the angle was exactly right. Okay, but as we've seen, these things can all change. Okay? Now, let's just have an example. And we've looked at these before, right? If I'm going faster than the optimum speed, what's happening, right? Well, that additional speed, it's pushing me out further, right? The centripetal force is not enough to try and compensate, and that's why it's going further and further away, okay? So therefore, what you're going to experience is a force in, now you're in the car, right? And you've played corners before. You're going faster and faster, and you take the corner. Which way are people inside the car being flown? Which way? The outside of the turn, right? Because guess what? You, passenger, you have inertia as well. And just like the car before, you want to go off in a tangent, and that's out of the circle, okay? So you got what we call a lateral force, okay? Lateral just means sideways. You would think, oh, sideways, that means horizontal, but we don't want to use that word, right? Because horizontal here means that way. So you've got a lateral force upwards, away from the ground, I guess. But you can imagine the reverse situation. If you take this and, you know, grandpa's driving or something like that, and I'm like, no, I don't want to take this curve so fast. Okay, so the opposite will happen, okay? You're going to have a lateral force, but it's going to be downward, okay? Now, just like in other situations where you got up and down, you can define whichever you want as positive and negative, so long as you're consistent and you say what you're doing, okay? But the point is that we've got this new axis involved here, and it's perpendicular to the, should have labeled, perpendicular to the normal force. It's along the road, okay? That's the lateral force you experience. So let's have a look at this example. I've given you a road radius. Don't worry about the mass of the car, we don't know what it is. Let's have gravity 9.8. And the road designer has designed the curve so the optimum velocity you're meant to take, so this is obviously a highway road, is 120 kilometers per hour, right? So here are our questions. Number one, if 120 kilometers per hour is the optimum speed, how far should I make the embankment, right? And then secondly, what happens at these speeds? What happens if some hoon comes around and ignores the speed limit and goes at 180 kilometers per hour around the corner instead? What lateral force will they be experiencing? Which way and how much? And then likewise, if grandpa comes along and wants to go slower, which way will he experience a force and how much? Okay. So let's have a look at this. First thing you've got to do is all of these units, they're not in SI, they're not in meters or in seconds, right? So therefore, I'm going to start off by saying, okay, here's part A. R, that radius, I want that in meters, don't I? So, R equals 1,000. Okay? I also want the velocity in meters per second, right? So the velocity is, well, how many meters in 120 kilometers? 120,000, right? And then it's over how many seconds in an hour, and the answer is 3,600. That's meters, and that's seconds. Okay, I think it works out to, is it 50? Is it 50? No, it's another awkward number. It's 100 on 3. That's right. I'm thinking of part B. Okay, so now I've worked out those in the right units. Okay, go back to what we looked at in the ideal world, because that's what this is talking about, the ideal theta. Okay, tan theta, no, hold on, other way around, v squared. V squared is equal to, I think we said, what was it, Rg tan theta? Is that what you've got? Rg tan theta, right? So theta is what I'm trying to find. I'll just sub everything in. You've got 100 on 3 squared. That's 1,000. That's 9.8. Yeah. Rearrange a little bit. What's 100 squared? 10,000, right? 10,000. So you'll have 10 left. 3 times 9.8. Whip out your calculator. What do you get for theta? Let's do nearest minute. Nearest minute? Anyone got it? What have I got? Where? What? Oh, yes, sorry, it is 9. Square. With the right numbers in it. Someone got a, do tan inverse, what do you get? I'm expecting a pretty small angle. Cool, yeah, I think that's about right. You're a spinner. Okay, so far so good. So this is our ideal world. We've got the right speed, okay, and we've decided what the angle of the road is. So now, this is true for the rest of the question, okay, so we can take that, right? Now let's have a look at part B. Part B. And we've got this guy coming around at 180 kilometers per hour, right? So that's going to be 180,000 on 3,600 meters per second. And I think this is the 50 that I was thinking. Times 5? Yeah, I think it works out, okay? So what happens at this point, okay? Being that things are not going to balance out nice and neatly anymore, we're going to get something like this, okay? So I want to account for this lateral force, right? So which way would you like to define as positive? Which way do you want? Do you want it to be up or do you want it to be down? Up? Okay, sure. So let's make that positive. Okay, so now what I'm going to do is I'm going to draw myself a new diagram, okay? So like that one, but with all of these numbers on it, okay? So let's see here. I'm going to go over here. Okay, now, there's the normal force, right? But I'm not going to worry about that too much. What I'm really interested in is the lateral force, because I've already worked out all the bits, the n cos theta and the n sin theta for the normal force. That's okay, right? So if I have the lateral force going up in this direction, okay? Now when I want to resolve it, I'm going to have horizontal and vertical part. So get your horizontal here. And you've got a lateral vertical part here, okay? So use your geometry. You got your theta there, which we already know, 6 degrees, 28 minutes. Corresponding angles, so I see there's a theta there and a theta there, okay? So what do you work out your horizontal part of the component to be? Horizontal component. That's adjacent, right? It's adjacent, so I think you're going to get L cos theta there, going in that direction. Conversely, you have L sin theta going upwards. Okay. Now, you already worked out before what your normal forces will be. I think you've got N cos theta going that way and N sin theta going this way. So now when I resolve everything vertically, what's going on? Vertically, what's going on? You got the lateral force going upwards, and you have the normal force also going upwards, right? So I think we're going to get L sine theta plus N cos theta. Is that right? Yeah. And that should be counteracting gravity. Yep. Let's call that 1. Horizontally, what's happening? Now these forces are acting in opposite directions, right? So I've got L cos theta going in the positive direction. Now, hold on a second. We define L cos theta going positive this way, right? But in our normal situation, right, horizontally, I think of the force toward the center as positive, right? So this would be negative, wouldn't it? It's going away from where the normal's going. Okay, so that means I'll put the normal first. Maybe I should have done that over here. Minus L cos theta, right? Whichever way they're going in opposite directions, okay? So that's mv squared on r. Okay, now, what are we trying to work out? I'm trying to find out what's the lateral force, how much is it, and which direction is it facing. So in other words, you're solving for L. Okay, and you've got these two equations to use. I want you to have a think about this for a second. I'll let you have a go, take a couple of minutes. What are you going to do to equations 1 and 2 so that you can solve for L? Remember, M is a constant, so you don't need to worry about it. We know what G is. We know what V is, or rather, that's what V is in this case. And we know what the radius is, okay? So how are you going to get all of the other stuff, the n's and the thetas, out of the picture and just have L? The problem we are encountering is that 1 and 2 are hard to put together, right? But it's not so bad. I mean, when you see something like this, for instance, some awkward number, or x. Okay? You're like, all right, well, if I'm going to put these two equations together, I'm going to need to eliminate something, right? And the way you would do it here is, well, for instance, suppose you wanted to eliminate y, okay? If I want to eliminate y, what I'll do is I'll take this whole thing and I'll multiply it by 2. And then I'll take this whole thing and then I'll multiply it by 5. Then I'll have a minus 10y here, a plus 10y here, I'll add them, and then poof, it's gone, okay? That's not so hard, okay? You have exactly the same scenario here. It's just that instead of numbers, you've got fluffy letters and Greek stuff, okay? But that's all right. It works in exactly the same way. Watch. Let's take equation 1, right? What I want to get rid of is the n cos theta, okay? And I see there's a n sine theta here. So I don't need to multiply by n. That's common. But if I multiply this one by sine and this one by cos, then they'll be the same, just like these would be the same. And then I can subtract, okay? So I'll take equation 1 and I'll multiply that one by sine. And then I'll take away equation 2 multiplied by cos, okay? If I do that, watch what happens, right? Well, you'll get L sine squared there, right? You'll have an n sine theta cos theta subtracting an n sine theta cos theta. So they're just gonna go, okay? There's minus, and then that's a negative, so double negative. So I'll have plus L cos squared theta. Oh, how convenient, okay? So that's good, that's good. What am I going to have over here? Well, I multiplied things, so that makes it a little bit messier, but that's okay. You're going to get what? mg sine theta minus mv squared on r cos theta. Is that all right? You happy with that? Okay, let's just tidy up a little bit. Sine squared plus cos squared, that just gives you 1. I'll just take out m. I mean, it doesn't make it a huge amount neater, but you are going to have m in the final equation because it's just a constant, right? So you have nothing to evaluate that with. M sine theta, sorry, g sine theta, v squared on r cos theta. Okay, cool. Now the good thing about this equation here, maybe it's worth putting a box around, right, is that it's irrespective of v. So I can take my two values of v and then just put them into the same equation, and then I can get a value for L. Okay, so in the case of part 1, what I would do is I say L equals m, it's just going to stay there, 9.8 sine, what was theta again? Like 6 degrees, right? 28. Minus, okay, this time I decided that V was 50. R is 1,000, right? And you go cos the same angle, okay? Now once you get out the end, let's just round it off a little bit, you get minus 1.38 m, I think, okay? Now, m's going to be positive, right? It's a mass. So then what does this mean? Which way is this force facing? And you have a look and it's going downward. Okay, why is that? Why is L going downward? We said if you go faster, you get pushed outwards, right? Now, inertia is pushing you out that way. But this force is actually friction. This is what we started with. This is the thing that's keeping you, if there was no bank, right? If it was just going around, right? Then friction is what keeps your wheels on the ground. Remember that situation we were looking at before? It was optimum speed, it was perfect, everything balanced out. But if everything does not balance out, then you're gonna have friction. Quite a lot of it, okay? Depending on the mass of your car, right? Now just a quick note. This friction is acting in that way, and the faster I go, the more friction will be acting that way, which is why if you've ever been driving along on a highway or something, and you're looking at the road, and on the road in front of you, you can see there are tire marks, right? These kinds of things. What does that mean? Where did they come from? Okay? Well, intuition tells you someone took this corner and they took it too fast, right? The faster you take it, the more friction there will be. And friction, as you know, it's a force, it causes energy, it's hot, right? So it burns off part of the tires, and that's where they are, right? Because they took the corner at a speed that was higher than the optimum, okay? So the friction is acting downwards, otherwise it'd just fly off, okay? Now, if we replay this situation, okay, and all we have to do to get a new speed is, well, this is half. It's exactly half. So all I have to do is adjust this number. That's convenient. Okay. And when you do that, what do you get? 0.52 or something? Okay. So as you'd expect this time, friction is still doing its job, but what it's doing is it's acting upward. It's stopping your car from sliding down the hill because you're going too slow. Hurry up, okay? But you see what's going on, right? Too slow, friction's got to act up. If you think about it this way, if you just stopped on the hill, right? Just motionless, okay? Friction is acting on you. Otherwise, you're going to slide down the hill. If there's not enough friction, you just roll down, just like my keys rolled off the diary, okay? But if you're going, it won't be so bad, but there will still be some friction keeping you up in that direction. Otherwise, you'll slide down the hill, okay?